If every road on Earth vanished tonight, the Milky Way would still stretch so far that even light itself would need about 100,000 years to cross it. What looks like a quiet band of stars in the night sky is actually a galaxy so vast, so layered, and so difficult to imagine that the human mind almost refuses to hold its scale. Tonight, this journey begins at the fading edge of the Milky Way and moves slowly inward toward its hidden center. If deep space stories like this are worth exploring, please like the video, subscribe to the channel, and stay with us as we cross the galaxy in thought. Far beyond the bright band that crosses the night sky, the Milky Way begins to lose its clear outline. From within it, the galaxy appears as a soft river of light, broken by dark lanes of dust and scattered with brighter knots where stars gather in greater number. Seen from inside, it does not offer the neat shape of a diagram. It surrounds the observer in every direction, and its true size must be learned slowly, through patient measurement of stars, gas, motion, and light. At its broadest level, the Milky Way is a barred spiral galaxy, a vast rotating system of stars, gas, dust, and unseen mass spread across a disk with curving arms and a faint outer rim. Yet the word edge can be misleading. A galaxy like this does not end with a sharp boundary. It thins, it fades. It grows sparse over enormous distances, until one region gives way to another so gradually that the act of drawing a line becomes more a matter of definition than of sight. The outermost visible disk of the Milky Way is often described as extending for about 100,000 light-years across, though some measurements suggest that its full stellar and gaseous structure reaches farther. This means that a straight crossing from one far side of the disk to the other would require a journey of roughly 100,000 light-years, and perhaps more, depending on which outer structures are counted. Even at the first step, the scale is difficult to hold in the mind. A light-year is the distance light travels in 1 year, moving through empty space at the fastest speed known in nature. Light itself, so quick across ordinary earthly distances, needs about 100,000 years to pass from one broad side of the Milky Way disk to the other. The number does not merely describe size, it describes a failure of common habits of thought. Roads, oceans, continents, and even the orbits of planets do not prepare the mind for such a span. At the galaxy's far rim, stars are much less crowded than in the inner regions. The outer disk contains older stars, thin clouds of gas, and occasional pockets where new stars still form, though less actively than closer in. The structure here is faint and delicate. It does not resemble a wall. It resembles a slow thinning of matter spread through space. A traveller crossing this region would not encounter a boundary gate or a final luminous band. Instead, the surroundings would become more empty, with wider gaps between stars and fewer dense clouds of gas. The galaxy would feel less like a packed city and more like a rural plain at night, with long distances between isolated points of light. This outer realm is also not perfectly flat. The Milky Way's disk is warped, bent slightly upward in some directions and downward in others. Astronomers detect this by tracing the position of gas clouds and stars far from the centre. The warp means the galaxy's outer shape is not a clean mechanical circle. It is a living structure shaped by gravity, motion, and interactions over long stretches of cosmic time. Nearby dwarf galaxies, streams of stars left behind by past encounters, and the pull of dark matter all play roles in shaping the outer form. The result is that even the phrase across the Milky Way needs care. Across which line, through which plane, and from which outer point to which other outer point all matter. The answer changes with the path chosen. Still, for the broad human imagination, the outer disk provides the first true sense of the problem. To cross the Milky Way is not merely to pass through a field of stars. It is to move through a system so large that any familiar speed becomes almost motionless when placed beside it. A modern spacecraft, moving faster than any ordinary vehicle on Earth, would remain deeply confined within a tiny local region even after many human lifetimes. At speeds reached by present space missions, the time needed to cross the galaxy would stretch into spans so long that civilizations would rise and vanish long before any such trip could be completed. Even when imagined at much greater speeds, far beyond present engineering, the crossing remains measured not in days or years, but in ages. The outer edge also resists easy observation because the Milky Way is not studied from outside. No telescope has travelled far enough to photograph the whole galaxy from a distance. Its form is reconstructed from inside, using many kinds of evidence. Radio observations trace cold hydrogen gas far beyond what visible light can easily show. Infrared light reveals stars behind dust. Motions of stars and gas reveal how mass is distributed. Distances are measured through careful methods that build outward step by step. In this way, the Milky Way's edge is not found by sight alone, but by combining many partial views into one coherent picture. What emerges is not a single bright border, but a broad frontier where matter becomes sparse and structure turns faint. In that faint frontier, the meaning of emptiness also changes. Space between stars is still not truly full in the ordinary sense, yet it contains thin gas, dust grains, magnetic fields, energetic particles, and the gravity of the galaxy as a whole. The outer disk is a low-density environment, but not an absence. It is a vast medium, stretched across distances that make even tiny amounts of matter significant when gathered over thousands of light years. The stars there continue to orbit the galactic center, though the rotation does not follow the simple pattern once expected if only visible matter were present. Their motions helped reveal one of the deepest facts about the Milky Way. Much of its mass is invisible. The outer edge, faint as it is, becomes one of the places where the hidden structure of the galaxy first makes itself known. So the journey begins not in brightness, but in thinning light. The Milky Way at its broad outer limit is a place of sparse stars, warped structure, faint gas, and uncertain boundary. It is the first layer in understanding how long a crossing would take, because before motion can be imagined, the scale must be accepted. The galaxy is not a glowing wheel with a neat rim. It is a vast and fading disk whose outer regions already exceed ordinary comprehension. To stand at that edge in thought is to realize that the crossing is enormous before it has even truly begun. Beyond the fading rim of the Milky Way's disk, the galaxy does not simply end. It opens into a much broader and more diffuse region known as the halo. In astronomy, a halo is the wide, roughly spherical envelope that surrounds a galaxy beyond its bright central body. The Milky Way's halo is vast, faint, and difficult to see directly as a single structure, because it is not made of one smooth shining shell. It is traced instead through scattered stars, ancient globular clusters, thin streams of stellar debris, hot gas, and the invisible pull of dark matter, which appears to supply most of the halo's mass, where the outer disk still gives the impression of a flattened galactic body. The halo begins to remove that familiar shape. Here the Milky Way becomes less like a wheel and more like a great gravitational domain, extending far beyond the shining band that human eyes associate with the galaxy itself. The stellar halo is thinly populated when compared with the disk. Its stars are old, often poor in heavier chemical elements, and spread across immense distances. Many of them appear to be remnants of the early history of the galaxy, formed in small systems that later merged into the growing Milky Way. Observations indicate that parts of the halo preserve that ancient record. Their motions differ from the more orderly rotation of stars in the disk. Rather than moving together in a relatively flat, shared pattern around the center, halo stars follow a wider variety of tilted and elongated paths. This gives the halo a looser and more scattered character. A traveller moving through it would not see a rich field of nearby stars in all directions. Instead, the stars would often be separated by broad reaches of darkness, each point of light standing alone across an almost unimaginable emptiness. Among the most visible inhabitants of the halo are the globular clusters. These are dense spherical groups of very old stars, bound tightly by gravity and orbiting the Milky Way far above and below the disk. Some contain hundreds of thousands of stars packed into relatively compact volumes. Against the sparse background of the halo, they stand out as remarkable structures, like islands of concentrated starlight in a largely empty sea. They're among the oldest known objects associated with the galaxy, and they help astronomers map the halo's extent and mass. Yet even these clusters, impressive as they are, occupy only tiny points within the vastness of the halo. The distances between them remain immense. Their presence does not make the halo crowded. It only adds a few bright markers within a region defined mostly by separation. The halo also contains streams of stars, long-stretched ribbons left behind as smaller galaxies or clusters are torn apart by the Milky Way's gravity. These streams reveal that the halo is not a quiet and untouched shell. It is a place where past encounters remain visible for long spans of time. As smaller systems fall inward, the galaxy's tidal forces pull them apart. Their stars do not vanish. They spread along orbital paths, creating extended structures that can be traced across the sky. In this way, the halo records the Milky Way's growth through accretion, the slow gathering of smaller bodies into a larger whole. The halo is therefore not only outer space around the galaxy, it is also a memory field, preserving evidence of how the galaxy assembled itself over billions of years. There is also gas in the halo, though much of it is extremely thin and very hot. This gas does not shine brightly in visible light, and for a long time its full presence is difficult to measure. Modern observations suggest that a large reservoir of diffuse hot gas surrounds the Milky Way, extending far beyond the disk. Its density is low, but its total extent is so large that it may contain a substantial amount of matter. This halo gas interacts with inflowing material from smaller galaxies, and with outflows driven from the disk by stellar winds and supernova explosions. The halo is therefore not completely detached from the main body of the galaxy. Matter moves through it, cools, mixes, and sometimes returns inward. Even so, the halo remains an environment of extraordinary thinness. Any crossing through it would be defined less by encounters with objects and more by the endurance of distance. Most of all, the halo is where the hidden mass of the Milky Way becomes impossible to ignore. The visible stars and gas in the disk do not seem to provide enough gravity to explain how fast outer material moves around the galaxy. Observations of orbital motion indicate that the Milky Way is embedded in a much larger halo of dark matter. Dark matter is the name given to matter that does not emit, absorb, or reflect light in any directly observed way, but whose gravity influences stars, gas, and galaxies. Its nature remains uncertain, but its effects are measured through motion and structure. In the Milky Way, dark matter appears to form the dominant mass of the halo, extending far beyond the visible galaxy. This means that a true crossing of the Milky Way, understood in terms of its full gravitational reach, could be much larger than a crossing of the bright disk alone. Estimates of the Milky Way's dark matter halo extend to several 100,000 light-years from the center, and some definitions place its outer influence farther still. The exact boundary remains uncertain, because dark matter does not present a visible edge. Its presence is inferred, and the transition between the Milky Way's halo and the broader environment of the local group is gradual. Still, what is clear is that the bright disk familiar from night sky imagery occupies only a fraction of the galaxy's full domain. If the disk suggests a crossing time of around 100,000 light-years at the speed of light, the halo suggests a much greater scale depending on where the journey is said to begin and end. Yet within this outer envelope, there is little visual drama. The halo expands the galaxy not by filling space with spectacle, but by filling it with reach. This changes the emotional meaning of the crossing. In the disk, distance is tied to visible structure stars, arms, gas, and dust. In the halo, distance becomes quieter and more abstract. The galaxy remains present through gravity, even when its luminous body has grown faint. A traveller in the halo would still belong to the Milky Way long after leaving the bright disk behind. The crossing would continue through a dominion that feels almost empty, yet is still shaped by the galaxy at every point. In that sense, the halo teaches a deeper lesson about scale. The Milky Way is not only what shines, it is also what holds. Around the Milky Way, beyond the broad outer halo yet still held within its gravity, smaller galaxies move in long and patient orbits. These are the satellite companions, dwarf galaxies that travel around the larger system and help define the true scale of its influence. They are not part of the main disk, and they do not blend smoothly into its spiral structure. They are separate stellar systems, each with its own history, its own dark matter content, and its own fragile balance between internal gravity and the pull of the Milky Way. Their presence shows that the galaxy is not an isolated island in space. It is the dominant body in a surrounding family of smaller companions, and the distances between them add a further dimension to the idea of crossing from outermost realm toward inner light. Some of these satellites are visible to the naked eye from dark southern skies. The Large Magellanic Cloud and the Small Magellanic Cloud appear as misty patches of light, detached from the Milky Way's luminous band. They are nearby dwarf galaxies, rich in gas and young stars, and they provide one of the clearest examples of companions still actively shaped by their relation to the Milky Way. Other satellites are much fainter, discovered through deep surveys that reveal sparse groupings of ancient stars spread across the sky. Many dwarf galaxies are small in mass and low in brightness. They can be difficult to find, not because they are rare, but because they are dim and diffuse. Their faintness reflects the modest scale of these systems compared with the giant spiral galaxy. Yet their importance is great. They serve as markers of the Milky Way's gravitational domain and as evidence of the long process through which large galaxies grow. A dwarf galaxy is a galaxy much smaller than the Milky Way, often containing far fewer stars and less gas. Some retain active star formation, while others are quiet systems dominated by old stars. Their shapes vary. Some are irregular, lacking a smooth form, while others are more rounded and diffuse. What unites them is their relative smallness and their sensitivity to outside forces. The gravity of the Milky Way can distort them, strip away their gas, and gradually unbind their stars. In this way, the satellites reveal not only the size of the galaxy's reach, but also its power. A companion that wanders too close does not remain unchanged. It begins to stretch, to lose matter, and sometimes to dissolve. This process leaves behind stellar streams, long ribbons of stars that arc through the halo. A stream forms when a dwarf galaxy or globular cluster is pulled apart by tidal forces, the difference in gravitational pull across its body. The stars that once belonged to one compact system begin to spread along its orbit, tracing its path over great distances. These streams are among the most delicate structures known around the Milky Way. They can be thin and faint, visible only through careful mapping of stellar positions and motions, yet they are powerful tools for understanding the galaxy, because their shapes respond to the distribution of mass through which they pass. In other words, they act as subtle probes of the Milky Way's gravitational field. The streams do not simply decorate the halo, they measure it. The Sagittarius dwarf spheroidal galaxy provides a clear example of this slow destruction. It orbits the Milky Way and is being torn apart, leaving streams of stars wrapped around the galaxy. The process is not sudden. It unfolds across many orbital passages and vast stretches of time. The dwarf galaxy remains partly intact even as it is scattered. This reveals something essential about galactic crossing. Space on these scales is not a place of abrupt collision in the ordinary sense. The stars are too far apart for that to be common. Instead, systems interact through gravity over immense intervals, changing shape and losing matter long before any dense central encounter takes place. A traveller passing through the realm of these streams would be moving through evidence of ancient disruption stretched thin across the halo, where the past remains written in stars. The satellite system also helps astronomers estimate the mass of the Milky Way. By measuring the motions of dwarf galaxies and streams, researchers infer how much gravity is required to hold them in orbit. These measurements suggest that the Milky Way is far more massive than its visible stars and gas alone would indicate. Much of that mass appears to lie in dark matter, extending across the halo and governing the paths of companions far from the disk. The satellites therefore serve as moving test particles, each one responding to the hidden structure of the galaxy. Their orbits are not always known with full precision, and some details remain uncertain, especially for the most distant and faint companions. Even so, observations consistently indicate that the Milky Way's sphere of influence extends far beyond its luminous body. This surrounding population of companions makes the galaxy feel less like a single object and more like the centre of a system, the crossing. When imagined from the widest practical edge, is no longer just a passage from one side of the bright disk to the other. It begins in a region populated by small neighbouring galaxies, each separated from the next by tens of thousands or even hundreds of thousands of light years. The emptiness between them is still overwhelming, but it is not meaningless emptiness. It is shaped by gravity, traced by orbital motion, and marked by the slow exchange of matter. Gas can be drawn away from a companion. Stars can be stripped into streams. Dark matter halos can overlap and interact. The outskirts of the Milky Way are therefore not static. They are active on long timescales, governed by steady motions too slow for direct human perception, but clear in the accumulated evidence of astronomy. The Magellanic Clouds themselves are linked to a larger structure of gas known as the Magellanic Stream, a long trail extending across a large portion of the sky. This stream likely forms through tidal interaction and the removal of gas by motion through the hot halo medium. It shows that a companion galaxy can leave behind not only stars, but also immense reservoirs of gas spread over great distances. Such structures make the outer Milky Way a more connected environment than simple images of isolated points might suggest. The companions are separate, but not wholly detached. They influence and are influenced by the main galaxy in ways that slowly reshape both sides of the relationship. To move inward from this region is to leave behind the broadest neighbourhood of the Milky Way and enter a more continuous galactic body. Yet here, among the satellites, one essential truth becomes clear. The Milky Way is large enough to hold other galaxies in orbit. Its crossing cannot be understood only by the span of visible starlight. It must also be understood through gravitational reach, through the companions that circle it, and through the streams that reveal how far its power extends into surrounding space. The far outer disk of the Milky Way stretches inward from the fading frontier into a region that is still unmistakably part of the galaxy's main body, yet already thin, quiet, and widely spaced. Here the disk is present not as a bright crowded lane, but as a broad stellar plain. It remains flattened. It rotates around the galactic centre, and it contains stars, gas, and dust arranged within the general shape of the galaxy's spiral form. Even so, this outer disk is gentle in appearance. The stars are fewer than in the inner galaxy. Clouds of cold gas are spread thinly. The great brightness that fills many images of the Milky Way belongs elsewhere. In this region, a crossing remains defined above all by distance itself, because the galaxy's disk has begun in earnest, but its density is still low enough that the emptiness between its contents remains the dominant fact. The outer disk is important because it marks the point where the Milky Way becomes more than a gravitational domain and more than a halo scattered with ancient objects. It becomes a structured rotating disk of matter. A disk galaxy is a system in which many stars and gas clouds orbit within a broad, flattened plane. In the Milky Way, this plane extends across vast distances. The far outer parts are still bound into that shared form, though not with the same richness seen farther inward. The stars here tend to be more sparsely distributed, and many are older populations orbiting steadily through the galaxy's outskirts. Some younger stars are present as well, because star formation is not absent, but it is generally less common and less intense than in denser spiral arms nearer the centre. This region is also where the disks warp and flare become more noticeable. A flare means that the disk grows thicker at greater distances from the centre, with stars and gas spreading farther above and below the central plane. In the far outer Milky Way, the disk is not simply a thin sheet carried unchanged to its rim, it bends and broadens. Observations of hydrogen gas, especially through radio astronomy, reveal these distortions clearly. The galaxy's outskirts are shaped by long interaction with companions, by the pull of the dark matter halo, and by the internal motions of the disk itself. As a result, the path across the outer disk is not a perfectly level road. It runs through a structure that is wide, faint, and slightly uneven, more like a stretched fabric than a rigid wheel. Hydrogen gas becomes one of the main ways this region is studied. Much of it is neutral hydrogen, meaning ordinary hydrogen atoms that are not ionized. This gas emits radio waves at a very specific wavelength, allowing astronomers to trace it even where visible starlight is weak. In the far outer disk, the hydrogen extends farther than much of the bright stellar population. It outlines the Milky Way as a rotating gaseous system larger and more expansive than a simple map of visible stars would suggest. This is one reason estimates of the galaxy's full disk size vary. The stellar disk and the gaseous disk do not fade in exactly the same way, and both can reach beyond what the eye alone would imagine. A crossing measured through the outer gas may therefore be longer than one measured only by the brighter concentration of stars. Even in this sparse region, motion remains organized. The outer disk continues to orbit the galactic center, and its rotation carries stars and gas at speeds that reveal the underlying mass of the Milky Way. One of the major discoveries of modern astronomy is that this rotation does not slow in the way once expected at large distances. The outer parts move faster than visible matter alone seems able to explain. This is one of the clearest signs that dark matter surrounds and penetrates the galaxy on large scales. In the far outer disk, then, the visible thinness of the region can be misleading. It appears sparse, but it moves within a gravitational field much stronger than the brightness of its stars would suggest. The outer disk is a dim place carried by an invisible foundation. If a crossing were imagined through this region, the experience would not resemble a passage through a dense forest of suns. It would resemble long travel across an enormous plain where stars appear as separated settlements in a dark landscape. The distances between neighbouring stars remain very large, and the distances between significant clouds of gas can also be immense. Most of the volume is still open space, yet this open space is inside the galaxy's main disk, and that matters. A traveller here would be moving through a region where the Milky Way's flat rotating body is unmistakable, where the shared orbital pattern of the disk governs the motion of matter, and where the galaxy's great width begins to feel not like an estimate but like a lived condition. The far outer disk also preserves clues to the history of the galaxy. Because it is more weakly bound and less dense than the inner regions, it can retain signs of past disturbances, waves, ripples, and asymmetries in the stellar distribution may record the effects of interactions with dwarf galaxies or passing streams of matter. The outer disk is therefore sensitive. Small gravitational nudges that might be less obvious in crowded inner zones can leave clearer marks here. This makes the region valuable for understanding how the Milky Way has changed over time. It is not merely the edge of something stable, it is a responsive outer layer, still settling and still bearing the imprint of encounters. There is also a difference between how the outer disk looks from far away and how it would feel from within. In a distant image of another spiral galaxy, the outer disk can appear as a graceful fading boundary, almost decorative in its softness. From inside, that same region becomes a prolonged environment. Its faintness does not shorten it. On the contrary, it deepens the impression of scale, because there are fewer bright landmarks to break the continuity of distance. The crossing continues through long reaches where structure is present but subdued, and where the galaxy reveals itself by persistence rather than spectacle. So the far outer disk is the first true stretch of the Milky Way's body, thin yet organized, faint yet immense. It carries stars, gas, motion, and memory, all arranged within the flattened form of the galactic disk. The outermost uncertainty of the boundary now gives way to a more continuous terrain, but not to a crowded one. The crossing remains slow in the imagination, because the galaxy has become more solidly defined without becoming small. Here the Milky Way begins to feel less like a distant object and more like a place through which one could travel for ages and still remain far from its centre. In the outer disk, the Milky Way is broad and quiet, but as the crossing moves farther inward, a larger pattern begins to emerge from the thin spread of stars and gas. The disk is not uniform. It is arranged into spiral arms, long curving regions where gas, dust, and stars gather more strongly than in the spaces between them. These arms are among the defining features of spiral galaxies. Yet they're not rigid objects like the spokes of a wheel. They are patterns within the rotating disk, shaped by the movement of matter and by large-scale gravitational effects. In the outer Milky Way, the spiral structure begins to show itself more clearly, not as a sharply outlined design visible to the eye from within, but as a gradual increase in material, cloud by cloud and star-forming region by star-forming region, along great arcs that wrap around the galaxy. A spiral arm is a region of enhanced density within the galactic disk. Density here means that stars, gas, and dust are somewhat more concentrated than in surrounding areas. The increase is enough to matter greatly, even though the space between stars remains enormous by ordinary standards. In these arms, giant clouds of gas can collect, cool, and collapse into new stars. Dust becomes more abundant. Bright young stars, especially massive ones, help mark the arms because they shine intensely and do not live long enough to drift far from the places where they are born. This is why spiral arms often appear bright in photographs of other galaxies. They are not made only of newborn stars, but those young luminous stars make the arms easier to trace. In the outer Milky Way, several major spiral arms extend through the disk. Their exact number and detailed form remain areas of active study, because the galaxy must be mapped from within, and because dust blocks visible light across large regions. Even so, observations in radio, infrared, and other wavelengths indicate a broad spiral pattern, including features known as the Perseus arm and the outer arm, along with additional structures that may be full arms or smaller spurs and branches. The uncertainty is not about whether the Milky Way has spiral structure. That is well supported. The uncertainty lies in the fine map, in the exact continuity and strength of each arm, and in how the bar at the centre helps organise the pattern farther out. The galaxy offers a real spiral form, but not one so simple that every line can be drawn with complete confidence. The outer spiral regions are shaped strongly by gas. Cold molecular clouds and neutral hydrogen gather along these long arcs, and where conditions allow, gravity draws parts of those clouds inward until star formation begins. A molecular cloud is a cold, dense cloud where hydrogen exists mainly in molecular form, paired into molecules rather than remaining as separate atoms. These clouds are important because stars are born within them. The outer arms therefore become places where the galaxy renews itself. They're not only structural features, they're active zones in which raw material is turned into stars, planetary systems, stellar winds, and eventually the enriched gas that later generations of stars will inherit. A crossing through these regions would still be dominated by emptiness, but it would also pass through some of the most visually rich environments of the outer galaxy. The spiral pattern does not mean that the same stars always remain inside the same arm. The disk rotates, and stars orbit the centre at speeds that differ from the speed of the spiral pattern itself. One useful way to think about the arms is as traffic waves in a crowded flow. The cars move forward, yet the wave of congestion can persist as a pattern through which individual cars pass. In a galaxy, the comparison is only partial, but it helps clarify the main idea. Gas and stars move through the spiral arms. As gas enters an arm region, it can be compressed, helping trigger the birth of stars. Then, as stars continue along their orbits, they may leave the arm behind. The arm is therefore not a solid object rotating as one piece. It is a sustained region of enhanced density and activity. Because of this, the crossing of the Milky Way through its spiral structure is not a passage through fixed walls, but through changing zones of greater material richness. The difference matters. A traveller moving across an arm would not encounter an unbroken barrier of light or matter. Instead, there would be a larger number of gas clouds, star-forming regions, dust lanes, and bright young stars spread across many light years. The region would be more textured and more varied than the sparse outer disk, but it would still be largely open space. Even within the arms, stars are separated by tremendous distances. The richness of the arm lies in relative concentration, not in crowding by everyday standards. The outer spiral arms also give the first strong sense that the Milky Way is a living disk rather than a static arrangement. Massive young stars in these regions emit strong ultraviolet light, ionizing surrounding gas and creating glowing nebulae. Stellar winds push on nearby material, supernova explosions, the violent ends of some massive stars, stir and enrich the surrounding medium. These events inject energy into the interstellar gas and help shape future generations of clouds. The arms are therefore places where the galaxy's material cycle is more visible. Gas gathers, stars form, stars alter their surroundings, and matter is returned in changed form. The crossing inward now passes through a region where time is written not only in motion, but in repeated processes of formation and release. From within the Milky Way, however, the arms are not easy to see as graceful spirals. Dust obscures long stretches of view, and perspective compresses distant structures into overlapping bands. Astronomers reconstruct the pattern through careful measurements of gas clouds, star-forming regions, masers, star clusters, and stellar motions. A maser is a natural source of amplified radio emission, often found in star-forming regions, and it can be measured with great precision to determine distance and motion. Such methods have greatly improved the map of the Milky Way's spiral structure. They show that the galaxy's arms are not merely imagined from analogy with other spirals. They are real, though not simple, features of the disk. So in this part of the crossing, the Milky Way becomes more visibly organized. The broad plane of the far outer disk gathers into curving lanes of gas, dust, and stars. Spiral structure begins not as decoration, but as a new level of order in the galaxy's main body. The journey inward is still measured in enormous spans, but now it moves through regions where matter is more strongly shaped into arcs of activity. The galaxy is no longer only wide. It has begun to show its pattern. Between the spiral arms, the Milky Way opens into quieter stretches of the disk. These interarm regions do not lack matter, but they hold it in a thinner and less dramatic form. The bright clusters of young stars become less common. Dense molecular clouds are fewer. The glowing signs of recent starbirth fade, and the galaxy settles into a wider, calmer rhythm. Yet this quieter space is not empty. It is filled with diffuse gas, fine dust, magnetic fields, cosmic rays, and older stars moving along their orbits through the disk. The crossing inward now passes through one of the most important truths about a galaxy, even where the pattern relaxes. The distance does not. Between the arms, the Milky Way continues for enormous reaches, and the long, calm intervals between richer structures become part of the real measure of its breadth. The term Interarm region refers to the space between major spiral arms. In a simple picture of a spiral galaxy, the arms may seem to contain the galaxy while the spaces between them seem secondary. In reality, the interarm zones make up a large part of the disk. They are not blank gaps cut out of the galaxy. They are wide regions through which stars and gas continue to move. Many stars, including older populations like the Sun, spend much of their orbital lives in such areas. The galaxy here feels less concentrated, but not absent. Light remains scattered across the sky. The disk still has depth and structure. It simply expresses them more gently. Diffuse gas is one of the defining features of these quieter lanes. Diffuse means spread out and low in density. Instead of gathering into thick cold clouds, much of the gas in interarm space exists in thinner forms, sometimes warm and neutral, sometimes ionized, sometimes mixed with hotter material created by past energetic events. The interstellar medium, the matter between stars, is not made of one single substance in one single condition. It exists in several phases, each with different temperature and density. In the interarm regions, these phases blend into a broad and subtle environment. A traveller moving through it would encounter no visible ocean of substance, because even this gas remains extraordinarily thin by earthly standards. Yet over thousands of light years, such tenuous matter becomes a major component of the galactic disk. Dust is present here as well, though often in a less dramatic form than in the denser arms. Dust in astronomy means tiny solid particles, made of elements such as carbon, silicon, oxygen, and iron, mixed through the gas. These grains are small, but they matter greatly. They absorb and scatter starlight, especially at shorter wavelengths, and they help cool clouds so that gravity can more easily gather gas into denser structures. In the interarm lanes, dust still dims and reddens light from distant stars, but it usually does so more softly than in the thick, dark lanes associated with major cloud complexes. The result is a region that may appear more transparent than the arms, yet is still shaped by fine material spread across vast distances. Magnetic fields also thread the space between the arms. These fields are weak compared with those of ordinary magnets on Earth, but they extend over huge scales and influence the motion of charged particles and gas. They help shape the structure of interstellar matter, guide cosmic rays, and contribute to the broader behavior of the disk. Their full role in spiral galaxies remains an area of active research, but observations show that the Milky Way's disk is magnetized, including in its calmer interarm zones. This adds another layer to the idea of crossing. The galaxy is not just a collection of stars and clouds scattered in a vacuum. It is also a physical medium with invisible order, where matter, radiation, and magnetic structure interact continuously. Older stars become more prominent in these regions. Massive blue stars, which burn brightly and live briefly, tend to stay near the star-forming arms where they are born. Longer-lived stars have more time to drift away from those nurseries and move through the disk. As a result, the interarm regions often contain a higher relative share of mature stellar populations. These stars still orbit the galactic center in the flattened disk, but their surroundings are less crowded by bright nebulae and dense birth clouds. The light of the galaxy here becomes steadier and less dominated by youth. It is a quieter starlight, spread across distance rather than gathered into active knots. This changes the character of the crossing. The spiral arms introduce visible pattern and concentration, but the interarm regions restore the long continuity of travel. They remind the mind that a galaxy is not crossed arm by arm alone. It is crossed through the immense spaces between them, where there may be fewer spectacular structures but no relief from scale. If anything, the quietness makes the distance feel larger. In a more active region, bright landmarks break up the imagination. In calmer space, the crossing extends through long intervals with fewer signs of change. The galaxy seems to breathe more slowly here. The interarm regions are not permanently fixed as quiet lanes. Gas flows, stars orbit, and the spiral pattern moves in relation to the material of the disk. Over long spans of time, gas can gather toward denser regions, while stars pass from arm to interarm space, and later encounter another arm. The Milky Way is therefore not made of static compartments. It is a rotating system in which matter continually changes position. Still, at any given moment, the interarm zones remain recognizable as the broad, quieter stretches between the more concentrated arcs. They are part of the galactic pattern precisely because they contrast with the arms while remaining fully within the disk. Supernova remnants and bubbles of hot gas can also drift into or expand through these calmer regions. A supernova remnant is the expanding material left after a star explodes. Over time, such events stir the interstellar medium, heating some areas, compressing others, and helping create cavities surrounded by denser shells. Even in the quieter interarm lanes, the galaxy bears traces of past activity. The calm is real, but it is not lifeless stillness. It is a broad equilibrium shaped by motion, pressure, radiation, and the remains of older events. So this part of the Milky Way is defined not by absence, but by gentleness. Between the arms, the disk stretches onward through diffuse gas, soft dust, magnetic structure, and mature starlight. The great crossing continues through lanes that seem quieter only by comparison. They are still enormous, still active in slow ways, and still fully part of the galaxy's body. Here the Milky Way reveals that its size is not carried only by its brightest features. It is carried just as much by the long quiet spaces in between. Within the broad disk of the Milky Way, between the more massive spiral arms, there lies a smaller structure often called the Orion arm, or Orion spur. A spur is a lesser branch of a spiral pattern, not as large or as strongly defined as a major arm, yet still a real concentration of stars, gas, and dust within the disk. This is the local spiral region that contains the solar system. It is not at the centre of the galaxy, and it is not placed in one of the grandest arms. Instead, it occupies a modest position between larger spiral features, most often described as lying between the Sagittarius arm inward and the Perseus arm farther outward. The importance of this region comes not from its size, but from its familiarity. It is the part of the Milky Way known most directly through close observation, and it gives the crossing a local anchor, a place where the enormous abstract map of the galaxy touches the neighbourhood of the Sun. The Orion arm is not a major spiral arm in the same sense as the larger structures that help define the Milky Way's pattern. It is smaller, less extended, and more irregular in shape. Even so, it is far from insignificant. It contains many stars, several notable star-forming regions, and large clouds of gas and dust. It may be best understood as a local segment of enhanced density, a bridge-like feature within the wider spiral arrangement. Because the solar system lies inside it, much of what human astronomy first learns about the Milky Way comes from looking out through this region. Nearby bright stars, nebulae, open clusters, and dark clouds are often part of this same local structure, from the ground. Before the full galactic pattern is understood, these nearby features naturally dominate human awareness of the galaxy. The Sun is located about 26,000 light-years from the galactic centre, though exact estimates vary slightly with method. That distance places it well away from the central bulge and far inside the outer disk, in a middle region of the Milky Way where the disk is neither especially sparse nor especially crowded by galactic standards. The solar system orbits the centre along with the surrounding stars and gas, carried within the disk at a great speed. Yet the orbital period is so long that one full revolution takes on the order of more than 200 million years. This means that the local region feels stable on human timescales, even though it is in steady motion through the galaxy. The crossing inward has now reached a zone where the Milky Way is experienced not as a distant object, but as the immediate stellar environment in which the Sun lives. The local spiral region contains many familiar astronomical landmarks. The Orion Nebula, one of the most studied star-forming regions in the sky, lies within this broader neighbourhood. So do the Taurus molecular clouds, the Pleiades cluster, the Hyades cluster, and many nearby bright stars that shape the constellations visible from Earth. These objects do not define the entire Orion arm, but they illustrate its character. It is a region rich enough to produce young stars and nebulae. yet not so dense as to resemble the deeper inner galaxy. It holds both mature stars and active nurseries. The result is a mixed environment in which calm stellar neighborhoods exist not far from clouds still engaged in star formation. The local region therefore offers a good example of how the Milky Way combines stability and renewal within the same part of the disk. Because the solar system lies within the disk, much of the night sky is shaped by perspective through local structure. Looking along the plane of the galaxy means looking through many more stars, clouds, and dust lanes than looking above or below it. The bright band of the Milky Way is therefore not only a sign of the galaxy's total population, it is also a sign of where the line of sight passes through the greatest thickness of the disk and through local concentrations of matter. In the Orion region, nearby stars can appear prominent even if they are not especially large or luminous compared with more distant galactic populations. Nearness grants them weight in the sky. This is one reason the local region is so visually important. It shapes the human experience of the galaxy from the inside. A crossing of the Milky Way that passes through the Sun's neighborhood gains a more intimate scale for a moment, though only by comparison. The distances between nearby stars are still immense. Even within the local region, the nearest star system beyond the Sun lies more than 4 light-years away. Star-forming clouds span dozens to hundreds of light-years. Open clusters can contain stars spread across similar scales. The Orion arm itself extends for thousands of light-years. So even here, in what may be called the local district of the galaxy, the sense of size remains overwhelming. Familiarity does not make the region small. It only makes its vastness easier to picture because some of its objects have names, measured distances, and well-studied forms. This region also helps clarify a common misunderstanding. The solar system is sometimes imagined as sitting in a special central lane of the Milky Way, or in a prominent arm from which the whole galaxy can be surveyed. In fact, the Sun occupies a fairly ordinary location in a secondary structure. This is scientifically significant because it shows that the galaxy does not require a privileged location to produce stable planetary systems and long-lived stars. The Sun's neighborhood is dynamic enough to include star formation and interstellar clouds, yet not so extreme as to expose it to the intense crowding and radiation more typical of the deeper inner regions. Observations indicate that this middle disk environment has likely been relatively favorable for long-term planetary stability, though many details of the solar system's full galactic history remain uncertain. The local spiral region is also important for mapping the Milky Way itself. Distances to nearby stars can be measured with especially high precision, and those measurements provide a foundation for the larger cosmic distance scale. Radio observations of local molecular clouds, infrared surveys through local dust, and precise motions from space observatories all contribute to a sharper picture of how the Orion arm fits into the wider galactic design. In this sense, the local region serves as both home and reference point. It is where the map begins, not because it is central, but because it is near. So the crossing has reached the Sun's spiral neighborhood, a modest spur within the larger disk, rich with nearby stars, clouds, and star-forming regions. The galaxy here is neither remote nor extreme. It is immediate, structured, and still immense. In this local arm, the Milky Way becomes a place with known landmarks, but the great scale of the crossing remains untouched. Even home is built on distances that far exceed ordinary imagination. The solar neighborhood is the region of the Milky Way immediately surrounding the Sun, a local volume of space filled with nearby stars, faint clouds of interstellar gas, traces of dust, and the quiet motion of objects sharing the broader orbit of the galactic disk. It is the most familiar part of the galaxy. not because it is small, but because it can be studied with the greatest precision. Distances here are measured more directly. Stellar motions can be followed more accurately. Individual stars can be examined not as distant points within a crowded background, but as distinct suns with known positions, temperatures, masses, and ages. Yet this familiarity can create a false impression of nearness and comfort. The solar neighbourhood is local only by galactic standards. It remains a region of immense separation, where even the closest stars are divided by distances that light needs years to cross, and where the crossing of a modest nearby portion of the Milky Way already stretches far beyond the scale of human travel. The nearer stars to the Sun form no tight cluster in the ordinary sense. They are spread through space with large gaps between them. Proxima Centauri, the closest known star to the Sun, lies a little more than 4 light-years away. Its companion stars, Alpha Centauri A and Alpha Centauri B, form a nearby multiple star system, but even this nearest neighbouring system remains separated from the Sun by a gulf so wide that all ordinary planetary distances disappear into insignificance beside it. Beyond these lie other nearby stars such as Barnard's star, Wolf 359, Sirius, Epsilon Eridani, Tau Ceti, and many more, each with its own motion through the galaxy. Some are red dwarfs, small and faint stars that are common throughout the Milky Way. Others are brighter and more massive. Together they reveal that the local region is not uniform. It is a mixed stellar environment, quiet in density, varied in character. Most stars in the solar neighbourhood are not bright giants or short-lived massive stars. They are smaller, longer-lived stars, especially red dwarfs. A red dwarf is a cool, low-mass star that burns its fuel slowly and can remain stable for extremely long spans of time. Their abundance means that the local Milky Way is filled less with brilliant suns than with dimmer ones. Many are too faint to be seen with the unaided eye despite being relatively nearby. This matters for the imagined crossing because it shows that even a local region can contain many stars while still appearing sparse and dark to human vision. Brightness does not measure fullness very well. The solar neighbourhood contains a substantial stellar population, but it is distributed so widely that open space remains the dominant feature. The stars of the solar neighbourhood are not fixed in a static pattern. Each one moves with its own velocity through the galaxy, though many broadly share the rotation of the Milky Way's disk. Over long spans of time, constellations slowly change shape as their stars drift along different paths. Some stars pass closer to the Sun over millions of years, while others move farther away. This local motion adds depth to the idea of neighbourhood. It is not a set arrangement of permanent nearest stars. It is a flowing galactic environment in which distances and relative positions gradually evolve. The Sun itself moves through this region, carrying its planets with it while also oscillating slightly above and below the galactic plane as part of its larger orbit. Interstellar gas in the solar neighbourhood is thin, but it is not absent. The Sun currently lies within a region often described as the local interstellar cloud, itself part of a broader cavity known as the local bubble. A cloud in this context does not mean anything like an earthly cloud. It means a low-density region of gas and dust spread across interstellar space. The local bubble appears to be a large cavity of unusually hot, tenuous gas, likely shaped by ancient supernova explosions that cleared and heated the surrounding medium. Within or near this cavity lie smaller cloudlets of cooler material, including the one through which the solar system is moving. These structures show that even the immediate surroundings of the Sun are part of the dynamic interstellar medium, shaped by past stellar events and ongoing galactic motion. The local bubble is especially important because it reminds the mind that even calm local space has a history. Supernovae, the explosions of dying stars, can reshape nearby interstellar matter on scales of hundreds of light years. Their shock waves compress some clouds, disperse others, heat gas, and enrich space with heavier elements. The present local environment may therefore be the product of older episodes of stellar birth and death that occurred in nearby associations of massive stars. Observations support this general picture, though some details of timing and structure remain under study. The solar neighborhood is calm now by comparison with more active star-forming zones, but it bears the imprint of earlier disturbance. Dust in the local region is patchy and relatively modest compared with the thicker lanes seen along other parts of the galactic disk. This is one reason the nearby stars can be observed so clearly. Still, local dust matters. It affects starlight, contributes to the chemistry of interstellar space, and marks the presence of colder, denser pockets where stars may eventually form. Not far from the Sun in galactic terms are molecular clouds such as those in Taurus and Ophiuchus, regions where star formation continues within the broader local spiral environment. The solar neighborhood is therefore not cut off from the larger life of the galaxy. It is a relatively gentle sector embedded within a wider disk that still produces new stars and reshapes its gas. The spacing of stars here offers one of the clearest ways to understand how difficult even a modest galactic journey would be. If the imagined crossing paused to consider only the local neighborhood, the challenge would already be immense. Light takes years to move between the nearest stars. Spacecraft built by human engineering take far longer still. The width of a local cloud, the diameter of a nearby stellar grouping, or the distance to a nearby nebula all extend beyond ordinary travel by extraordinary margins. This is the scale on which the Milky Way begins to become personally real. The galaxy is not only vast in its far spiral arms and hidden halo, it is vast in the immediate surroundings of the Sun. So the solar neighborhood is a place of measured familiarity and persistent enormity. Its stars are known more intimately than any others beyond the Sun. Its interstellar medium has been mapped in unusual detail, and its motions help define the local frame from which the wider galaxy is understood. Yet nothing in this familiarity reduces the distance. The nearest part of the Milky Way already surpasses ordinary imagination. The crossing inward continues. But here it becomes unmistakably clear that even the home district of the galaxy is built on separations vast enough to humble every common sense of scale. The Milky Way is often imagined as a flat spiral, a wide shining disk spread across space like a thin wheel of stars. This image is useful at first, but it is incomplete. The galaxy has width, yet it also has depth. Its stars do not all remain in one perfectly narrow plane. They occupy layers above and below the central midline of the disk, and those layers differ in age, motion, and composition. As the crossing continues inward, the attention now turns from the broad stretch across the disk to its vertical thickness, because a real passage through the Milky Way involves not only movement from outer to inner regions, but also an understanding of how the galaxy is built in stacked bands of stellar matter. The disk is not a simple sheet. It is a layered structure with a thin disk and a thick disk, each carrying a different part of the galaxy's history. The thin disk is the flatter and denser component, the layer in which much of the Milky Way's gas, dust, and younger stars are concentrated. It is called thin not because it is small in ordinary terms, but because its vertical extent is modest compared with the full size of the galaxy. Many of the familiar features of the Milky Way belong to this thin disk: spiral arms, molecular clouds, open clusters, and regions of active star formation. The Sun is part of this component, orbiting within the disk while moving slightly above and below its central plane. In the thin disk, stars tend to follow relatively orderly orbits around the galactic center. Their motions are still complex, but they remain more closely tied to the flattened form of the galaxy than the older and more vertically extended populations beyond. Above and below the thin disk lies the thick disk, a broader stellar layer that contains older stars and reaches to greater heights from the galactic plane. A thick disk is not a separate galaxy or a detached shell. It is another component of the Milky Way's disk system, distinguished by its larger vertical spread and different stellar populations. Stars in the thick disk tend to be older and somewhat poorer in heavier elements than those in the thin disk. In astronomy, heavier elements means all elements heavier than hydrogen and helium, since those light elements dominate the early universe. A lower abundance of heavier elements usually indicates that a star formed earlier in cosmic history, before as many generations of stars had lived and died to enrich the gas. The thick disk therefore serves as an older record of the Milky Way's development. The exact origin of the thick disk is still studied, but observations suggest that it may have formed through a combination of early turbulence, mergers with smaller galaxies, and the long heating of stellar orbits over time. Heating in this galactic sense does not mean simple warming. It means the increase of random motion, causing stellar paths to become more tilted and more extended above and below the plane. A younger disk can begin relatively thin, with stars moving in more orderly flattened orbits. Later disturbances, including gravitational encounters and internal dynamical processes, can stir those orbits into a thicker structure. The Milky Way's thick disk therefore preserves signs of an earlier and more unsettled phase in the galaxy's life. This vertical structure changes the meaning of a crossing. A journey imagined only in the plane of the disk follows the broadest possible route through the Milky Way's main body. But the thickness of the disk shows that the galaxy is not a narrow line of travel. It is a layered volume. In the solar neighborhood, the thin disk extends for hundreds of light years in vertical scale, while the thick disk reaches much farther. The exact density of stars falls with height above the plane, but it does not vanish suddenly. Instead, the galaxy's disk gradually transitions from its crowded middle layer into sparser upper and lower regions. From inside the disk, this gives the Milky Way not only breadth, but body. It has an interior depth that becomes visible in the changing distribution of stars and gas. Dust and cold molecular gas are concentrated mainly near the plane of the thin disk. This is where star formation thrives most readily, because cold dense material is most available there. As one moves vertically away from the plane, such material becomes less common. The stellar population shifts toward older stars, and the clear signs of active formation diminish. This tells an important story about how the disk works. The middle layer is the most fertile and dynamic in terms of new stars and interstellar structure. The thicker layer is quieter, more ancient, and more shaped by long orbital history than by ongoing birth. So even within the same radial region of the Milky Way, conditions change with height. The galaxy is not the same at every level above and below its central plane. The vertical motions of stars also reveal that the disk is not rigid. The Sun, for example, does not travel in a perfectly flat ring around the center. It moves up and down through the galactic plane over long timescales while continuing its orbit around the center. Other stars do the same, some with larger vertical excursions than others. The thin disk stars usually stay closest to the plane. Thick disk stars wander farther. This creates a breathing quality in the galactic disk, not because the whole structure expands and contracts together in a simple rhythm, but because its members move in layered oscillations under gravity. The Milky Way's disk is a dynamic system of countless stars tracing paths that weave through a common gravitational form. The thin and thick disks also differ in brightness and visual character. The thin disk, rich in gas and younger stars, contributes strongly to the luminous band associated with the Milky Way in the night sky. The thick disk is dimmer and more diffuse, a more extended glow of older stars less sharply concentrated toward the plane, from a distance. Both contribute to the galaxy's visible body, but from within, the thin disk dominates the most dramatic views along the galactic plane. Even so, the thick disk matters greatly to the total mass and history of the Milky Way. It provides evidence that the galaxy did not form all at once in its present calm shape. It grew, settled, and was stirred. So the Milky Way now appears not merely as a widening spiral across space, but as a layered disk with structure above and below the plane. The crossing inward remains an immense horizontal journey, yet this section reveals that the path runs through a galaxy with thickness, age layering, and vertical motion. The thin disk carries much of the present activity. The thick disk carries the memory of older conditions. Together they give the Milky Way a fuller physical presence. It is not a flat picture, it is a stratified world of stars. As the crossing continues inward through the disk, the Milky Way grows more obscured. Light that seems continuous from a distance is interrupted by long, dark bands, dense patches, and irregular veils that lie across the galactic plane. These are the dust lanes and dark clouds, regions where fine solid particles and cold gas gather thickly enough to block or weaken the light of stars behind them. In visible light, they appear as gaps in brightness, as though the galaxy has missing pieces. Yet the darkness does not mark emptiness. It marks material. The light is there, but a curtain lies in front of it. In this part of the galaxy, the crossing becomes more complex because distance is no longer only a matter of how far the stars extend. It is also a matter of how much intervening material fills the space between them, shaping what can be seen and how the galactic interior must be understood. A dust lane is a relatively dense band of interstellar dust, often mixed with gas, that stretches along parts of the galactic disk. Dust in this setting means tiny grains of solid matter, formed from heavier elements released by earlier generations of stars. These grains are extremely small, yet when spread through great clouds across many light years, they become powerful agents of obscuration. They absorb and scatter visible light, especially blue light, leaving more red light to pass through. This is why distant stars seen through dust often appear dimmer and redder than they would in a clearer line of sight. In the Milky Way, dust lanes are especially noticeable along the galactic plane, where the density of interstellar matter is greatest. From Earth, they cut across the bright band of the galaxy like winding rivers of shadow. Dark clouds are denser local concentrations within this dusty medium. Some are large molecular cloud complexes extending across dozens or hundreds of light years. Others are smaller, compact globules where the gas and dust are thick enough to hide nearly everything behind them. A molecular cloud is a cold region where hydrogen exists mainly in molecular form and where densities are high enough for chemistry and cooling to proceed more effectively than in the diffuse interstellar medium. These clouds are important because they are the birthplaces of stars. The darkness they present to visible observation is therefore not a sign of inactivity. It often marks the very regions where the next generation of stars is beginning to gather from cold gas under the pull of gravity. In visible light, the effect of these clouds is dramatic. They break the smooth appearance of the Milky Way into uneven lanes and patches. Famous dark regions such as the Coalsack Nebula show how a nearby cloud can stand out clearly against a rich field of background stars. Larger cloud systems in the inner parts of the disk create even more extensive obscuration. From within the galaxy, this means that direct sightlines inward are limited. The central regions are heavily veiled by dust, and much of the Milky Way's true structure cannot be mapped by visible light alone. Infrared and radio observations become necessary because longer wavelengths pass through dust more easily. This fact has transformed modern astronomy. It reveals that much of the galaxy remains present behind the darkness, not absent from it. The dust itself is mixed with gas, and together they form a structured medium rather than a uniform fog. The densest parts are cold and clumpy. They can contain filaments, cores, and layered shells shaped by gravity, turbulence, magnetic fields, and radiation from nearby stars. Turbulence here means irregular motion within the gas, stirring it into patterns that are neither smooth nor entirely random. The result is a highly textured environment. Even within one cloud complex, some regions remain diffuse while others condense into knot-like cores that may collapse into stars. The crossing through such a zone is therefore not through a solid obstacle, but through a varied landscape of cold matter stretched across huge distances. These clouds also alter the rhythm of the galaxy. In clearer interarm regions, distant stars can be traced with relative ease. In the dark lanes, vision is shortened. One line of sight may end at a nearby dust wall, while another opens through a thinner window into deeper space. This makes the Milky Way from within a galaxy of partial views. The dust does not erase the structure, but it forces astronomy to reconstruct that structure through many indirect methods. Distances must be measured through radio emission from molecules, through infrared surveys of embedded stars, through parallax to nearby clouds, and through the motions of associated objects. The darkness therefore deepens not only the appearance of the crossing, but also the challenge of knowing what lies ahead within the disk. Within the clouds, chemistry becomes richer than in the more diffuse medium. Molecules such as carbon monoxide, water, ammonia, and many organic compounds can form and survive in shielded cold regions. These molecules do not make the clouds dense in an earthly sense, but they do indicate conditions where the gas is protected from the full force of starlight. Dust grains help in this process by providing surfaces on which reactions can occur and by reducing the penetration of energetic radiation. The cold interiors of dark clouds are therefore among the most chemically complex environments in interstellar space. They are quiet in temperature, obscure in light, and fertile in process. The presence of dense clouds also affects travel in a broader conceptual sense. The Milky Way is sometimes imagined as mostly empty with isolated stars scattered through it, and in many ways that is true. Yet these dark regions show that some parts of the disk contain substantial concentrations of matter spread across enormous volumes. A journey through them would not be a journey through blank vacuum alone. It would pass through clouds, gradients of gas density, dust-filled regions, and zones of star formation still hidden from direct view. The galaxy here feels thicker, not because stars are suddenly packed together like grains, but because the interstellar medium itself becomes a more visible participant in the structure of the disk. Many of these dark clouds are temporary in a cosmic sense, though long-lived by human standards. Stars forming within them can eventually light and disperse the surrounding material. Supernovae can tear through nearby regions and reshape the clouds. Galactic rotation can stretch and shear them. New clouds can also form from converging gas flows and from the compressed shells of older stellar events. This means that the dust lanes seen across the Milky Way are part of a cycle. Matter gathers, cools, collapses, forms stars, and is then altered again by the energy those stars return to the surrounding medium. The darkness is therefore not the end of light, but part of its preparation. So in this section of the crossing, the Milky Way becomes shadowed and materially rich. Dust lanes and dark clouds turn brightness into contrast, replacing open visibility with veiled depth. They hide the inner galaxy while also making it possible, because within these cold, dense regions the raw material of future stars collects and changes. The crossing continues inward through a disk that is no longer only marked by stars and spiral pattern. It is marked just as strongly by the dark matter of ordinary substance, the clouds that block sight even as they help build the luminous galaxy from within. Beyond the dark clouds and dust lanes, the Milky Way continues inward into regions where the spiral arms become richer, brighter, and more crowded with gas and stars. These inner spiral arms are not the center of the galaxy, but they are stronger expressions of the disk's organized pattern than the quieter structures farther out. Here the concentration of matter rises. Massive star-forming complexes become more common. The gas is more abundant, the background starlight thickens, and the sense of moving through a busy galactic environment grows more pronounced. The crossing now enters a part of the disk where the galaxy's structure appears more active and more luminous, yet still remains a disk of vast open separations rather than a continuous blaze. The inner arms reveal how the Milky Way can become denser without losing the enormous scale that defines every part of it. A spiral arm in these inner regions is still a zone of enhanced density rather than a rigid object. Gas and stars move through it, and the pattern persists through the disk. Yet the arms nearer the galactic center tend to hold more material and to support more intense star formation than many of the outer regions. This is partly because the inner galaxy contains a higher overall density of gas and stars. There is more raw material available, and the gravitational conditions of the disk are stronger. Giant molecular clouds become more frequent and often more massive. These clouds can give rise to clusters of bright young stars, ionized gas regions, and layered networks of dust and emission stretching across large parts of the arm. The inner Milky Way therefore appears more textured, more energetic, and more continuously structured than the quieter outskirts. One of the key differences in the inner spiral arms is the greater abundance of massive stars. Massive stars are those with much greater mass than the Sun, and though they live only brief lives in astronomical terms, they shape their surroundings strongly. Their radiation ionizes nearby gas. Their stellar winds push outward into surrounding clouds. Their deaths as supernovae inject heavy elements and energy back into the interstellar medium. In the inner arms, where star formation is more active, these effects become more frequent. This does not mean the galaxy turns violent in a constant visible sense. The scales remain too large for any one event to dominate the whole region, but taken together, the repeated presence of such stars gives the inner arms a more vivid and dynamically renewed character. The background light of the Milky Way also thickens here. In the outer regions, stars are numerous but widely scattered. In the inner arms, the line of sight passes through a denser stellar field. Even where dust obscures part of the view, the surrounding brightness grows. The disk feels fuller. Open clusters, loose groups of stars that form together from the same cloud, can be found in greater number, though many gradually disperse with time. Associations of young stars trace recent star formation, emission nebulae, glowing clouds of gas lit by hot nearby stars, become more common. The crossing therefore enters an environment where the signs of ongoing galactic life are repeatedly visible. Even if the whole arm still contains more empty space than matter by far. The gas in these inner arms is not spread evenly. It forms lanes, filaments, knots, and giant clouds. Some clouds remain cold and dark, still gathering material. Others are partly lit from within by newly formed stars. Some regions are carved by older stellar winds into shells and cavities. Turbulence, gravity, magnetic fields, and radiation all shape the medium. In astronomy, a filament is a long, narrow structure of gas or dust, often formed by flows, compression, or gravity acting across cloud material. Filaments are common in star-forming regions and can contain dense cores where stars begin to form. In the inner arms, such structures exist on large scales, woven through the broader pattern of the disk. This adds another level of complexity to the crossing. It is not simply a matter of moving through a brighter arm. It is a matter of moving through a layered environment where interstellar matter is constantly being rearranged. Orbital motion also grows more demanding to picture in these regions. Closer to the galactic center, stars and gas still orbit the center, but the conditions are shaped by the stronger gravitational pull of the mass within smaller radii. The orbital period becomes shorter than in the Sun's region, and the relative motions of gas, stars, and spiral pattern continue to create zones of compression and release. The inner arms therefore carry not only more matter, but a faster rhythm of circulation around the center. This does not shorten the crossing in any ordinary sense. It only means that the parts of the galaxy nearer the center complete their broad orbits in less time than the outer parts. The Milky Way remains a rotating system whose inner and outer regions do not all move in lockstep. Dust remains important here as well. In fact, some of the most prominent dust lanes of the Milky Way trace the inner spiral structure. They obscure deep views in visible light and help concentrate cold material from which stars can form. This means the inner arms often appear at once bright and hidden. Their star-forming regions shine strongly in infrared and radio observations, while visible light may be broken by dark barriers of intervening dust. Astronomers therefore rely on many wavelengths to study them. The inner arms are not guessed at from brightness alone. They are traced through molecular gas surveys, infrared star counts, radio measurements of star-forming regions, and the motions of gas clouds through the disk. The feeling of scale changes subtly here. In the outer regions, immensity is carried by openness. In the inner arms, immensity is carried by abundance. There is more to cross, not because the galaxy is wider here, but because the richness of material fills the imagination with a greater number of structures and processes. Yet the distances remain enormous. Giant clouds span tens to hundreds of light years. Stellar groupings spread across similar scales. The space between stars is still vast. The crossing inward does not become easier because the galaxy grows fuller. It becomes more layered, more luminous, and more difficult to simplify. So the inner spiral arms mark a new stage in the Milky Way's body. The disk is now denser, more active, and more continuously populated by gas clouds, young stars, open clusters, and dust-rich structure. The spiral pattern that first appears in the outer galaxy now reaches a stronger expression. Here the Milky Way shows its disk at greater intensity, not yet central, but clearly moving toward a brighter and more crowded interior. The crossing remains a passage through distance, but it now unfolds through arms where the galaxy's life is more strongly on display. As the crossing moves farther inward, the Milky Way becomes more crowded not only in gas and dust, but in stars themselves. The inner disk contains a much denser stellar population than the regions near the Sun or beyond. The line of sight through these areas grows thick with overlapping points of light, and the sense of open intervals between bright structures begins to weaken. This does not mean that stars now stand close together in the manner of ordinary objects on Earth. The separations remain immense, yet compared with the outer and middle regions of the disk, the inner galaxy is unmistakably fuller. The background glow strengthens, individual stars become harder to isolate at great distances, and the crossing takes on a new quality. Distance is no longer experienced mainly as emptiness between scattered objects. It is experienced as passage through a field of increasingly abundant suns. Stellar density means a number of stars within a given volume of space. In the outer disk and local neighborhood, that density is modest enough that large separations dominate any picture of travel. Farther inward, the number of stars per region increases. This happens because the galaxy's mass distribution becomes more concentrated toward the center. The disk itself grows richer, and the great bulging central population begins to contribute more heavily to the background. The increase is gradual rather than sudden. There is no single line where sparse space becomes crowded space. Instead, the galaxy thickens in starlight. Fields of stars become denser. The unresolved glow between brighter individual stars becomes more pronounced. The crossing inward is still measured in thousands of light years, but those light years now contain a steadily greater abundance of luminous bodies. This increase in stellar density changes observation as much as it changes imagination. In the solar neighborhood, nearby stars can often be studied against a relatively manageable background. In the inner disk, especially close to the plane, the number of overlapping stars becomes so large that separating one population from another requires careful measurement in infrared light, precise stellar motions, and statistical methods. Dust continues to complicate the view, but even where dust is less severe, crowding alone becomes a challenge. The Milky Way here is not merely distant, it is visually busy. One part of the difficulty in knowing the inner galaxy comes not only from what is hidden, but from what is too abundant to sort easily. The stars in these denser regions also represent a broad mixture of ages and types. There are young stars associated with spiral structure and star-forming regions, but there are also many older stars that have orbited the galaxy for billions of years. Red giants, evolved stars that have expanded after using much of the hydrogen in their cores, become more common in surveys of the inner galaxy because they are luminous and can be seen across great distances. Older main sequence stars, white dwarfs, variable stars, and compact remnants also fill the population. The inner Milky Way is therefore not simply brighter because it contains more stars, it is brighter because it contains more of nearly every category of star, layered together through long galactic history. With greater crowding comes a stronger radiation environment in some regions. Radiation here means the light and energetic particles produced by stars and stellar remnants. Most stars still lie far enough apart that direct danger from neighbouring stars would usually be small on the scale of a single planetary system. Yet in the inner galaxy as a whole, the chance of being relatively near energetic phenomena becomes higher simply because more stars, more star-forming regions, and more stellar endpoints occupy the same broad volume. Supernova, strong stellar winds, and intense ultraviolet sources are not constant everywhere, but they become less exceptional when the stellar field is richer. This does not mean the inner disk is uniformly hostile. It means that the environment becomes more complex as density rises. Gravitational complexity rises as well. In a sparse region, the motion of a star around the galactic center can be pictured mainly as a response to the galaxy's large-scale mass distribution. In denser regions, that large-scale pull still dominates, but local gravitational influences from nearby concentrations of stars, clusters, gas clouds, and spiral structure become more significant in shaping detailed motions. Over long timescales, such complexity can heat stellar orbits, scatter stars, and mix populations born in different places. The inner disk is therefore not only a place where there are more stars, it is a place where those stars participate in a richer web of interactions, not through frequent collisions, which remain rare, but through the cumulative effects of gravity across a crowded galactic environment. The meaning of distance changes again here. In the outer regions, one might imagine travelling for long periods with little visible change except the slow passage of isolated stars and clouds. In the denser inner disk, there would be more constant variation in the stellar backdrop. Dark clouds might interrupt one line of sight while bright stellar fields fill another. Clusters, associations, and luminous giants would become more frequent markers of place. The galaxy would feel less empty, yet not smaller. In fact, the abundance can deepen the impression of scale, because it reveals how much matter the Milky Way contains within its broad interior. The crossing is no longer only through space, it is through population. This richer field also carries the history of the galaxy's chemical evolution. Over time, repeated generations of stars enrich interstellar gas with heavier elements made in stellar interiors and explosive deaths. The inner galaxy, having hosted many such generations and generally possessing higher densities of star formation, tends to show greater chemical enrichment than more remote outer regions, though the pattern is not perfectly simple. This means that stars in the inner disk often form from gas that has been processed through many earlier stellar lives. The galaxy here is older in record and richer in material inheritance. The crossing inward is therefore also a passage through accumulated history, written not only in numbers of stars but in the chemistry they contain. Even so, the vast majority of space remains empty enough that direct encounters between stars are still exceedingly rare outside the most compact systems. This point remains essential. Greater crowding in a galactic sense does not mean closeness in a human one. The nearest star distances that seem enormous near the Sun remain large here as well, though averages may be somewhat smaller in denser zones. The inner Milky Way is not a packed swarm in which stars brush past one another like grains. It is a denser stellar landscape on a scale where light years are still the ordinary measure of separation. So the crossing now passes through an inner disk where stellar crowding becomes one of the galaxy's defining conditions. The Milky Way brightens through abundance. Its background glow thickens, its stellar populations overlap more deeply, and its gravitational and radiative environment grows more layered. The galaxy remains vast beyond ordinary understanding, but here that vastness is carried less by emptiness than by number. The inward path continues through a field of stars dense enough to change the character of the journey, while leaving its immensity untouched. Near the centre of the Milky Way, before the galaxy reaches its innermost stellar bulge and central black hole, there lies a remarkable inner reservoir of gas and dust known as the central molecular zone. This region occupies only a small fraction of the galaxy's total diameter, yet it contains an unusually large share of its dense molecular gas. A molecular zone is a region dominated by cold gas in molecular form, mixed with dust and organized into clouds, filaments, and clumps of exceptional mass and pressure. In the broader disk, molecular clouds appear in many spiral arms and star-forming complexes. But here the concentration rises sharply. The crossing inward now enters a realm where the interstellar medium itself becomes unusually heavy, compressed, and dynamic. The Milky Way is no longer only brighter in stars. It is thicker in raw material. The central molecular zone extends across the inner few hundred parsecs of the galaxy, though exact boundaries depend on how the region is defined. A parsec is a standard astronomical unit of distance, equal to a little more than 3 light-years. What matters most is not the precise edge, but the character of the region. Compared with the molecular clouds of the outer and middle disk, the gas here is denser, warmer, more turbulent, and subject to stronger tidal forces from the mass concentrated toward the galactic center. Turbulence means irregular internal motion in the gas, where material flows, collides, swirls, and compresses in patterns more complex than simple rotation or calm drift. In the central molecular zone, this turbulence is pronounced. The gas is restless on many scales, and the clouds are shaped by a demanding gravitational environment. The clouds here are among the most massive and extreme in the Milky Way. Some contain enormous quantities of gas packed into relatively compact regions, far denser than typical interstellar material. Yet this does not always translate directly into rapid star formation everywhere. Observations indicate that parts of the central molecular zone hold vast amounts of gas that seem capable of forming many stars, but the actual rate and distribution of star formation remain more complex than simple density alone would predict. Some clouds appear to be on the verge of widespread collapse, while others seem more resistant, held up by turbulence, magnetic fields, or internal pressure. This makes the region scientifically important. It shows that dense gas is necessary for star formation, but not sufficient by itself. Conditions within the gas also matter greatly. Dust is abundant throughout the zone, mixed tightly with the molecular material. It blocks visible light so effectively that much of the inner region is hidden from ordinary optical observation. Infrared, radio, and sub-millimeter astronomy become essential here, because longer wavelengths can penetrate dust more successfully and reveal the structures inside. Through those methods, astronomers detect long filaments of gas, compact dense cores, expanding shells, and stream-like flows moving through the inner gravitational field. The central molecular zone is therefore not a smooth ring or a single cloud. It is a system of interacting structures, each responding to gravity, orbital motion, pressure, and energy from nearby stars. The orbital behavior of gas in this inner region differs from the simpler picture often imagined for the outer disk. The Milky Way contains a central bar, an elongated concentration of stars that influences the motion of gas and stars in the inner galaxy. Gas responding to the bar's gravitational potential can move along elongated paths, funnel inward, shock, and pile up in particular regions. The central molecular zone appears to be shaped strongly by this bar-driven flow. Rather than following only neat circular orbits, gas may stream inward along the bar and then accumulate into dense structures near the center. This makes the inner galaxy a place where large-scale galactic dynamics and local cloud physics meet directly. The crossing has now entered a zone where structure is not only denser, but also more strongly governed by the central architecture of the Milky Way. The conditions inside this region are physically more intense than those near the Sun. Temperatures of the gas can be higher, pressures greater, and the surrounding radiation and cosmic ray environment stronger. Cosmic rays are high-energy particles that move through space and can affect the heating and chemistry of interstellar material. In the central molecular zone, their influence may be significant, though the exact balance between cosmic rays, turbulence, magnetic fields, and stellar feedback remains an active area of research. What is clear is that the gas here lives in a more extreme state than the calmer clouds of the outer disk. It is denser, more agitated, and more deeply embedded in the central gravitational field. Star formation does occur in this region, and some massive young clusters are found there, but it is uneven and sometimes puzzling. dense clouds that would seem ready to produce many stars do not always do so at the expected level. In other places, bright star-forming complexes emerge with great intensity. This unevenness suggests that the inner environment both supports and complicates stellar birth. Compression may help gather gas, while turbulence and strong shear may resist collapse in some zones. Shear means the tendency of neighboring layers of orbiting material to move at different speeds or in different directions, stretching and distorting clouds. In the central galaxy, such effects can be substantial. The result is an environment where the raw ingredients for stars are abundant, but the path from gas to stars is not simple. The central molecular zone also includes prominent radio and infrared structures such as Sagittarius B2, one of the most massive star-forming complexes in the galaxy. Regions like this show how deeply active the inner gas can become. They contain dense cores, rich chemistry, embedded young stars, and complicated internal structure. Such places are laboratories for understanding not only the Milky Way, but also the centers of other barred spiral galaxies. Because the central molecular zone shares properties with the dense nuclear gas in external galaxies, it offers a nearby example of conditions that can be much harder to resolve elsewhere. For the imagined crossing, this region marks a major shift in texture. Earlier parts of the Milky Way are defined by long empty stretches punctuated by spiral structure, clouds, and increasing star density. Here, the interstellar medium itself becomes a dominant presence. Dense gas and dust are no longer scattered ingredients within a wide disk. They gather into a concentrated inner reservoir. The galaxy feels heavier, not because it loses its openness entirely, but because the material between stars claims a stronger share of attention. The crossing now passes through a compressed central environment, where gas, dust, motion, and gravity are all intensified. So the central molecular zone stands as the dense inner reservoir of the Milky Way, a region of massive clouds, rich dust, strong turbulence, and complex star formation. It is a place where the galaxy's bar, gravity, and interstellar medium come together in one compact and restless domain. The crossing inward has reached matter in one of its most concentrated forms within the galaxy's main body. Here the Milky Way prepares its final inner structure not through openness or spiral grace, but through dense and obscured accumulation. Inside the dense gas and dust of the central molecular region, the Milky Way swells into a different kind of structure. The flat dominance of the disk begins to soften, and a rounded central population of stars takes over. This is the galactic bulge, the packed inner concentration of mostly older stars that fills the central part of the galaxy with a thicker and more continuous glow. A bulge is the central stellar component of many spiral galaxies, rising above and below the disk and containing stars on a wider range of orbits than those in the flatter outer regions. In the Milky Way, the bulge is not a simple sphere. Observations indicate that it has a boxy, bar-linked shape, with stars arranged in a thickened central structure that reflects the galaxy's internal evolution. The crossing inward now enters the heartland of starlight, where the number of stars rises greatly and the galaxy's inner body becomes deeper, rounder, and more ancient in character. The bulge contains an enormous population of stars concentrated into the central few thousand light years. Many of these stars are old, formed early in the history of the Milky Way. Though the bulge is not made of one single age group, it is a mixed population with a strong older component and a complicated record of enrichment and motion. Compared with the disk, where stars tend to orbit in a more orderly flattened pattern, bulge stars follow a broader variety of paths. Their orbits can be elongated, tilted, and distributed through a three-dimensional central volume. This makes the bulge feel different from every region crossed before it. The galaxy is no longer mainly a layered disk of stars and gas. It is now a dense central stellar body in which the flat geometry of the outer Milky Way gives way to a fuller and more crowded spatial form. The light of the bulge is dominated largely by older stars, especially cooler stars that shine steadily for long spans of time. Red giants are prominent among them. These are stars that have expanded into a later phase of life after exhausting much of the hydrogen in their cores. Because red giants are luminous, they help astronomers trace the bulge even through difficult observational conditions. Infrared surveys are especially useful here, since dust along the line of sight still blocks much visible light. Through infrared observations, the bulge emerges not as a vague central brightening, but as a structured stellar population with shape, depth, and internal pattern. The Milky Way's bulge is therefore not merely inferred from the general increase of light toward the centre, it is mapped star by star through careful observation. One of the important findings about the Milky Way is that its bulge appears closely connected to the central bar. The bar is the elongated inner structure of stars that extends across the central galaxy and influences the motion of gas and stars. In many spiral galaxies, bars help redistribute angular momentum, move gas inward, and reshape the inner disk over time. In the Milky Way, the bulge shows a boxy or peanut-like form when examined in detail, especially from the pattern of stellar densities above and below the plane. This shape is thought to result from the vertical thickening of the bar during the galaxy's evolution. In other words, the bulge may not be only a relic of early galactic formation. A substantial part of its present structure may have grown from the inner disk itself as the bar evolved and thickened. This gives the bulge a dual significance. It preserves ancient stars, yet its shape also records long internal change. The stellar density in the bulge is far greater than in the solar neighbourhood or most of the disk. The sky in such a region would be filled with stars beyond easy counting, though even here the average separations between stars usually remain far larger than ordinary human intuition first imagines. The bulge is crowded in a galactic sense, not packed in a terrestrial one. Still, the increase matters profoundly. The crossing through this region would pass through a background of almost continuous stellar presence. The glow of unresolved stars would be strong. Distinct luminous giants, compact clusters, and variable stars would appear in great number. The inner Milky Way here becomes a place where abundance itself defines the environment. This abundance carries a rich chemical history. Many bulge stars are enriched with heavier elements, indicating that the central galaxy has undergone repeated generations of star formation and stellar death over long spans of time, yet the chemical pattern is not uniform. Observations reveal a mixture of stars with different compositions, suggesting a complex formation history involving both rapid early build-up and slower internal evolution. Some stars in the bulge seem to trace very old populations formed during the earliest assembly of the Milky Way. Others may be more closely connected to the evolution of the bar and inner disk. This complexity makes the bulge one of the most informative regions in the galaxy for understanding how a spiral galaxy builds its center. The bulge also changes the gravitational environment. Here the mass concentration rises sharply, and the central pull of the galaxy becomes more dominant. Stellar motions reflect this stronger potential. Velocity dispersions increase, meaning that stars move with a wider spread of speeds and directions than in the calmer thin disk. A velocity dispersion is a measure of how varied those stellar motions are within a population. In the bulge, that variety is substantial. The region is dynamically hot, not in the sense of physical temperature, but in the sense that stellar orbits are less orderly and more mixed. This dynamical character further distinguishes the bulge from the flatter, more rotationally organized disk outside it. Even with all this stellar richness, the bulge is not isolated from the rest of the inner galaxy. Dust lanes from the disk still cut across some lines of sight. Gas flows shaped by the bar continue to pass nearby. The central molecular zone occupies the innermost gas-rich environment, embedded within the broader gravitational context of the bulge. So the bulge is best understood not as a separate object placed inside the Milky Way, but as the thickened stellar heart of the same galaxy, emerging naturally from the inward increase of density and the long history of internal evolution. It is where the Milky Way's central light becomes dominant. For the imagined crossing, the bulge represents the last great stellar region before the final center. The outward galaxy is still present behind, carried in memory as halo, disk, arms, clouds, and local stars. But here, those long structures have given way to a concentrated inner heartland. The scale remains vast, though the crossing has narrowed into the most crowded part yet encountered. The Milky Way no longer feels like a wide spiral plane. It feels like a dense central world of old stars, layered light, and deep gravitational concentration. So the galactic bulge is the packed inner stellar body of the Milky Way, shaped by ancient populations and by the long evolution of the central bar. It gathers the galaxy inward into a rounded, boxy, and luminous concentration where stellar density, chemical history, and gravitational depth all intensify together. The crossing has now reached the crowded heartland of the Milky Way. Only the final central region remains. At the innermost known center of the Milky Way, buried behind thick dust and surrounded by one of the most crowded stellar environments in the galaxy, lies the compact radio source called Sagittarius A star. This is the region associated with the Milky Way's central supermassive black hole, an object containing about 4 million times the mass of the Sun. A black hole is a concentration of mass so dense that, within a boundary called the event horizon, gravity is strong enough that not even light can escape. Yet the black hole itself does not fill the whole central region in any ordinary visual sense. It occupies an extremely small volume compared with the galaxy around it. The vastness of the crossing now ends not in a giant wall or blazing core, but in a compact gravitational center surrounded by stars, hot gas, magnetic activity, and the remains of matter moving through the deepest potential well of the Milky Way. Sagittarius A star is not seen directly in visible light because dust in the galactic plane blocks the view. Its presence is known through radio, infrared, and X-ray observations, and most clearly through the motions of stars orbiting very close to it. Over decades, astronomers have tracked these stars and watched them follow rapid, curved paths around an apparently dark central point. These observations provide some of the strongest evidence that a supermassive black hole lies at the center of the Milky Way. The motions are too fast and too tightly bound to be explained by any ordinary cluster of dim stars or stellar remnants confined in the same small space. The simplest explanation consistent with the data is a black hole of immense mass concentrated into a tiny region. In this way, the center of the galaxy is known not by direct view of the black hole itself, but by the precise behavior of the stars around it. The stars nearest Sagittarius, a star form part of the nuclear star cluster, the dense central cluster of stars packed into the innermost region of the galaxy. This cluster is one of the most crowded stellar environments in the Milky Way. It contains old stars, young stars, stellar remnants, and gas, all moving under the strong influence of the central mass. Some stars orbit so close to the black hole that their periods can be measured in years or decades, rather than the immense millions of years associated with the Sun's orbit around the galactic center. This contrast is striking. The galaxy that takes more than 200 million years for the Sun to circle has, at its deepest center, stars racing around the central mass on human observable timescales. The change in scale is not a contradiction. It is a reflection of how sharply gravity increases near a concentrated mass. Even so, the black hole does not dominate the whole bulge or inner galaxy by itself. Its influence is strongest in the central parsecs, while farther out the combined mass of star, gas, and dark matter shapes the broader galactic structure. This is important for understanding what it means to cross the Milky Way. The galaxy does not narrow toward a point because everything is falling directly into the black hole. Most of the mass remains spread through the bulge, disk, halo, and interstellar medium. The black hole is the central anchor of the innermost region, but it is only one part of the galaxy's total mass. The crossing reaches it as the final center, not because it contains most of the Milky Way, but because it marks the gravitational heart around which the visible structures are organized. The environment around Sagittarius, a star, is active, though not as luminous as the centers of some other galaxies with more rapidly feeding black holes. The Milky Way's central black hole is presently in a relatively quiet state. It emits radiation, flares at times, and interacts with surrounding gas and magnetic fields, but it is not consuming matter at a high rate compared with the active galactic nuclei seen elsewhere in the universe. Observations indicate that gas does fall inward, and hot material in the region produces emissions across different wavelengths, yet much of the available matter does not plunge directly into the black hole. Instead, it may orbit, heat, flow outward, or remain in unstable circulation. The center is therefore dynamic without being continuously brilliant. It is active in measured and intermittent ways, not in the overwhelming radiance sometimes associated with feeding black holes in other galaxies. This final region gives a clear answer to the question of crossing, if the Milky Way is measured in terms of its main bright disk. A crossing from one far side to the other is on the order of 100,000 light-years. If broader gaseous and structural components are included, the effective span can become larger. If the full dark matter halo is counted, the galaxy's gravitational domain extends vastly farther still. But the path from outer edge to central black hole region followed inward through halo, satellite domain, outer disk, spiral structure, local neighborhood, thickening stellar populations, dense molecular gas, and bulge shows something more important than any single number. The Milky Way is not one kind of place from edge to center. It is a sequence of environments, each with its own density, motion, material, and time scale. To cross it is not merely to endure one long distance. It is to pass through changing forms of galactic existence. The center also reveals how small a human scale remains beside galactic structure. A spacecraft moving at the speeds achieved by present technology would require spans far beyond the duration of civilizations to approach even a small fraction of such a journey. Even light, moving at nature's limit, would need tens of thousands of years to arrive from the Sun to the center, and roughly 100,000 years to pass across the main disk. These numbers are not simply large. They place the Milky Way beyond all ordinary travel. The galaxy is not a destination in the everyday sense. It is the vast system within which all familiar destinations already exist. Yet the final inward approach to Sagittarius, a star, also gives the galaxy coherence. The outer halo, the satellites, the spiral arms, the local stars, the dust lanes, the inner gas, and the bulge are not separate wonders gathered by chance. They are parts of one galaxy organized around a common center. The crossing reaches that center and shows that all the diffuse outer scales and all the crowded inner ones belong to one gravitational whole. What begins as a fading edge ends as a compact dark heart. Between those two lies the full architecture of the Milky Way. So the crossing ends at Sagittarius, a star, the compact central region that marks the Milky Way's innermost gravitational center. Here the galaxy gathers into its deepest focus, around a quiet supermassive black hole surrounded by one of the densest stellar environments in the system. The answer to how long it would take to cross the Milky Way is written not only in years of travel, but in the layered immensity of the galaxy itself. The journey inward ends where the structure converges and where the full scale of the Milky Way becomes most complete. The Milky Way now grows quiet in the mind. Its outer edge has faded into halo light and distant companions. Its great disk has stretched through sparse stars, gentle spiral lanes, dark clouds, and the familiar district of the sun. Farther in, the galaxy has thickened into brighter arms, denser stellar fields, heavy central gas, and the old crowded bulge. At last it has come to rest at the compact center, where Sagittarius A star marks the deep gravitational heart around which the wider system turns. What remains most striking is not only the number itself, though the number is vast. A crossing of the main disk takes about 100,000 years at the speed of light, and far longer by any speed human machines now achieve. What matters just as much is the way that distance is built. It is built from thinning edges, broad silent regions, clustered arms, hidden dust, and layers of stars whose separations remain immense even in the crowded inner galaxy. The Milky Way is not one uninterrupted field of brightness. It is a long sequence of environments, each quieter or richer than the last, each adding its own part to the scale of the whole. The galaxy also becomes gentler when seen this way. It is too large for ordinary travel, too broad for quick understanding, and too old for any single life to contain. Yet it is orderly. Stars orbit, gas gathers and cools, dust dims the light and helps prepare new stars. Gravity binds the far edge to the central dark heart. Across the full span, the Milky Way remains one connected structure, turning slowly through space. In that slow turning, the thought of crossing becomes less like a journey to be completed and more like a measure of place. The galaxy is not merely something seen in the night sky. It is the vast home of the sun, carrying every local horizon inside a far larger calm.